everyone, and welcome to our calculus notes for section 3.6. Today we're talking about a summary of curve sketching. So we're basically going to take all the topics that we've been doing this chapter and put them all together at once to be able to sketch the graph of an equation. So first off, here we have our table, and it's oriented the same way as we've been doing, where we place our critical numbers here as points that we need to test, and then we also have intervals around these critical values. Now the critical numbers, you'll recall, are where f prime of x, or the derivative, equals 0. In other words, we get a flattening of the graph there, or does not exist. So that is our first step in finding these types of things. Now we also want to include places where f double prime, so the second derivative, equals 0. And there we can get possible points of inflection. So we definitely want to add these to our points that we're testing. Now the summaries here are going to show us what happens. So at a critical number, if the first derivative and the actual function don't exist, then we're going to say this is a vertical asymptote. Okay. At another critical number, we get a value for y, and the second derivative was positive. We're going to call that a relative minimum. Okay. At another critical number, we do get a value for y, and the first derivative was 0, but now the second derivative was negative. We call that a relative maximum. Now on our intervals here, if f prime is positive in that interval, then we say that the function is increasing. If f prime is negative, then we say the function is decreasing. Now if we look at an interval and the second derivative is positive, then we say it's concave upward. And if the second derivative is negative, then we say the function is concave downward. Now in this case right here, we had a second derivative that was 0, and this is going to be a possible point of inflection if f double prime of x switches signs around x. So let's just say there was a point right here where the second derivative was 0. Now the interval to the left, the second derivative is negative. So what this is saying is if this interval has a positive second derivative, this would become a point of inflection. Okay? If this were negative, however, this would not be a point of inflection. Alright, so we're going to use this table and hopefully our understanding of it to sketch a couple curves here. Now the example says to analyze and sketch the graph of this function right here. Now the first thing we're going to need to find is the first and second derivatives. And before we do that, I think I want to multiply this 2 out just to make it a little bit easier. So 2x squared minus 18 over x squared minus 4. So here we're going to find our first derivative. And then we also need to find our second derivative. So looking at the first derivative, we're going to have quotient rule. So it's our low function times the derivative of our high function minus the high function times the derivative of the low function, all over derivative of the low function squared. And we'll just reduce this down. Okay, so we'll actually multiply out here and get 4x cubed minus 16x. Here we're going to get minus 4x cubed plus 36x And remember, we don't want to actually square that. And here you can see the 4x cubes are going to cancel out, and then the x's are going to combine. So negative 16x plus 36x is just 20x over x squared minus 4 squared. Okay, so there's our first step. Now what we want to do is find these critical numbers. Now remember, it's where the numerator equals 0 and then where the denominator equals 0. Okay, so the numerator is going to equal 0 when x equals 0, and the denominator is going to equal 0 when x equals plus or minus 2. So this gives us our critical numbers of x equals negative 2, 0, and 2. All right, let's go ahead and find the second derivative now. So we're deriving this function right here. So here's our first derivative, and if we derive this one, we'll get our second derivative. So using the quotient rule, we get the low function times the derivative of the high minus the high function times the derivative of the low. So here, looks like we're going to have to use the chain rule, so we'll use the power rule first. So 2 times x squared minus 4, and then times the derivative of x squared minus 4, which is 2x. And all of this is going to be over the denominator squared, so now we just have x squared minus 4 to the 4th power. All right, and we'll clean this up a little bit now. So it looks like we can factor out a 20 and also an x squared minus 4. And we're going to be left with an x squared minus 4 in our first term. And it looks like a minus 4x in our second term. And again, this is all over x squared minus 4 to the 4th. And it looks like we can cancel out one of these x squareds here. So we're going to be left with 20. Okay, so that's gone. And then this x squared minus 4 minus 4x, that's going to be negative 3x squared minus 4. And it'll be x squared minus 4 cubed. Remember, because we got rid of one of the x squared minus 4's right there. So here is your second derivative. And we want to find where this equals 0 or does not exist. So we wanted to see where this equals 0, and if you analyze this graph, you can see that it's going to be opening down and the vertex is going to be at negative 4. And so this one is never going to equal 0, so we don't have to worry about that. And we also have to check where the denominator equals 0, and we can see that that's just going to be at x equals plus or minus 2, and we already have those points covered right here. Okay, so that's our first step, finding the first and second derivatives, and then finding the critical numbers here, and the testing points for possible points of inflection in the second derivative. Alright, so now that we've done the calculus work, we want to go ahead and fill out a chart like this, where we're going to compare the x value, the f of x, f prime of x, f double prime of x, and then write down the characteristics of the graph. So we have our critical numbers here, our testing values, and we have to leave room for intervals. So we'll leave room for an interval here, and we'll put our first testing value here at negative 2. We'll leave room for an interval. We'll put our next test value at 0, interval, next test value at 2. And then our intervals here, this is going to go to negative infinity to negative 2. This one will be negative 2 to 0. This one will be 0 to 2. This one will be 2 to infinity. Alright, so now we just need to test each of these in our function derivative and second derivative. So we need to pick something here. And in the intervals, let's not worry about our f of x here, but let's find our f prime of x. So if we pick something less than -2 in this equation, okay, we can see that when we square the x, that makes this part positive, and it's going to be greater than our 4. So that's going to keep the denominator positive, but the numerator here is going to be negative. So we know that our first derivative is going to be negative on that interval. If we try the second derivative, okay, if I square something, that's going to make that positive, and it's going to be greater than 4, so the denominator is positive. In the numerator, if I square a negative, right, it is going to become positive, greater than 4, and then if I multiply it by -3, that's going to make it negative right here. So the second derivative is negative. If you want, you can always plug in actual values into your first and second derivative, but we'll just leave it like that for now. Okay, next at -2, if we look, well, if we plug in -2, we get a domain error in all three of these. So we just say does not exist. Okay, on the interval from -2 to 0, now we're going to plug in something like -1. So we can see that when we square this, -1 squared is +1, but then we subtract here, we get a negative again, but then it's going to square, so it'll be positive. Then if we look at the numerator, if I put a negative in here, well, that's going to make the answer negative. So we do have a negative there. Now if we plug -1 in here, okay, it'll be positive. But then we subtract 4, so that makes it negative, and then we cube it, so we still have a negative in the denominator. In the numerator, -1 squared is positive, but then we multiply it by a -3. So now we have a negative divided by a negative, which is positive. Our test value of 0. This is one where we actually do want to find our f of x. So we're going to plug 0 in here. So we get 0 squared minus 9. And then 0 squared minus 4. So it looks like we get -18 over -4, which is 9/2. Then we already know, since this was a critical number, the first derivative was 0 here. And then our second derivative, if we plug in 0, we would get -4 and then -4 cubed. Okay, so it looks like a negative over a negative. This is again going to be positive. Now we'll test our next interval here. Between 0 and 2, let's plug in 1. So the same thing's going to happen here in the denominator. That's going to be positive, and then that's going to be positive. So our first derivative here is positive. And then for our second derivative, now we have 1 squared is 1, -4, so that is negative. And then this is a 1, so it's negative divided by a negative. And we still get positive there. If we plug in 2, remember that was another place where we had a domain error. So this does not exist here. And if we pick something greater than 2, okay, so we could pick something like 3. So 3 squared minus 4, that's positive, and that's positive. So the first derivative here is positive. If we try 3 here, 3 squared 9 minus 4, positive, that's positive. And then here, 3 squared 9, but then times a negative, so it's negative over positive, making this negative. At this point, once we have all of this information filled out, we can simply refer back to this chart right here to determine what's happening, the characteristics of the graph. Now you can either remember and know what's happening, which is a good idea, or you could actually memorize this chart. So I want to show you both ways how it works. So just looking at this one, this is an interval, and we have negative and negative going to a does not exist. So what that tells me, so interval with a negative and a negative, is that this function is decreasing and concave downward on that interval. So we can just abbreviate there, decreasing and concave downward. At DNE, if we look here, that is our vertical asymptote. We can just write VA for vertical asymptote, and then I actually want to write the equation of the vertical asymptote would be x equals -2. Okay, here we have a negative and a positive, so negative first derivative means decreasing, and then a positive second derivative. Now we have to be careful because this is on an interval, so that means concave upward. Here at a critical number, we do get the 0, and the second derivative is positive. So that would be this case right here. And this becomes a relative minimum. So we would just write relative minimum. And we do want to give the point, and that's why we plugged in 0 into our f of x so that we could actually get the point. So 0, 9/2. In this one right here, an interval, positive, positive, so that's increasing, and concave upward. Here, all DNE, so this is our vertical asymptote again, and the equation is x equals 2. And then on this interval, positive and negative, so this is an increasing function, but it is going to be concave downward. Alright, so a couple other things that we want to write before we can actually sketch this are listed here. The domain, well, it's all real numbers except -2 and 2. We also want to find our x-intercepts. So if we want to look for x-intercepts, we let y equal 0. So if we let y equal 0, let's go back to our function again. Okay. So we would just say 0 equals this guy. Well, that's going to equal 0 where the numerator is 0. And we can see that that's going to happen at 3 and -3. So we actually get the points -3, 0, and 0, 3. Then for our y-intercepts, you let x equal 0. So we're going to go ahead and plug 0 in for x here. And you can see we get 2 times -9 over -4, and that is 9/2. So it's 0, 9/2. And the last thing we need to check for is any horizontal asymptotes. And we remember our Bovo-Botten eats DC. So in this case, it looks like they're the same. So exponents are the same. That means we want to divide the coefficients. So just divide 2 by 1. And so we know we have a horizontal asymptote at y equals 2. All right, next we want to sketch this. First we can look at our domain and range where things are happening. So it looks like we need to go a little past -2 and 2. And then vertically, here's a point at 9/2. So we need to make sure that we get up high enough. So let's just break it down here, -1, -2, -3, that should be fine. And then on this side we'll do 1, 2, and 3. Then vertically, we need to make sure we get up to 4.5 here. So let's do 1, 2, 3, 4, 5. We can do that below too. Okay, now next what I usually do is draw in my asymptotes. So here is vertical asymptote at -2 and at 2. And then we have a horizontal asymptote at y equals 2. Kind of have that grid there. Now next, we can go ahead and put any of these points in. So like -3, 0, and 0, 9/2. And then 3, 0. Okay, and now we're going to follow this. So on this interval, we're decreasing and concave down. So we know we're going to be bounded by these asymptotes, decreasing concave down. So we're going to get something like this. Now in this interval here, we're decreasing in concave up, and we know that this is a relative minimum. So decreasing concave up looks like this. We hit our relative minimum, and now we're increasing concave up. So it goes up this way. All right, and then we have a vertical asymptote, and then we're increasing concave down, and we have to go through this point. So the only choice is right here. All right, and we'll notice that we had no points of inflection here because at no point did the second derivative equal 0, so we didn't have to worry about that. All right, I want you to go ahead and try example 2 on your own. So find your first and second derivative, all your critical numbers, and where the second derivative equals 0 to test for points of inflection. Then I want you to go ahead and fill out this chart. So list your critical numbers here and your intervals, and then find the signs of f prime and f double prime, and then write out your characteristics. Also find the domain, x-intercepts, y-intercepts, and all horizontal asymptotes. And then using the characteristics and a couple of the points, I want you to sketch a graph of this equation as well. When you're finished, go ahead and come on back and check your work. All right, welcome back. So you can check your work on finding that first derivative, and then you can find our critical numbers. We're at 2 and 0. And here you can check your work on finding the second derivative. And notice this function did equal 0 when x was 3 or x was 0. And so those would become test points as well. Moving on to analyzing then, we set up our test points 0, 2, and 3. And we got our intervals here. And then we just tested values in that interval. In this interval, in this interval, this interval. Okay, we also found the points here at 2 and 3. And then we analyzed. So negative, negative was decreasing and concave down. Here we had a vertical asymptote at x equals 0. Here this would be increasing and concave down. Here we would have a 0 and a negative, which means a relative maximum. Here a negative and a negative, decreasing and concave down. Here at this test point we did have a 0 here for our second derivative, and so we really had to test over here, and we see a negative and a positive. So because this went from negative to positive, it became a point of inflection here at 3, 2/9, and this was decreasing and concave up. We also found that domain x did not equal 0. We found our x-intercepts. We let y equal 0 here, and we solved, so x equals 1, so 1, 0. The y-intercepts, when we let x equal 0, we get a no solution, all right, because it wasn't in our domain, so we don't have a y-intercept. And here, this is big on bottom. You can see the x squared, and so that means that the horizontal asymptote will be at y equals 0. So we sketched out our asymptotes here. On this interval, decreasing concave down. On this increasing and concave down, and we had our x-intercept here. Then we hit our relative maximum at 2, 1/4. And here's our point of inflection. So here it was decreasing concave down, and it switched decreasing concave up. And so that made our point of inflection right here. And there's your graph.